Hello everyone. Today we are going to revise chemical bond with the help of PPT. Chemical bond lesson with the help of PPT. So what is chemical bond generally? The attractive force between the atoms in a molecule is called chemical bond. Chemical bond is of how many types? Different types of chemical bond we have. Ionic bond, covalent bond, coordinate, covalent bond. We also have what? Hydrogen bonding, metallic bonding. So different types of chemical bond we have discussed. Today we are going to revise the chemical bond topic. Suppose if you take what now the two atoms, if you take two atoms which are apart from each other, means away from each other. So now here we have taken on what energy is taken on y-axis and internuclear distance is taken on x-axis. Okay, so internuclear distance means distance between two atoms. Distance between two atoms or two nuclei. Between two nuclei, the distance is called what? Internuclear distance. And here energy is taken. So energy is measured in what now taken in kilojoules per mole, and the internuclear distance is nothing but the distance between two nuclei is taken in picometers. Suppose. Now initially, when two atoms, these two atoms are away from each other, what is the internuclear distance? So this much distance is there between them. So this is the distance between two atoms. So this much distance is between one nucleus and other nucleus. Internuclear distance is this much is there. They're away from each other, the two nuclei. Okay. Now here, there some amount of energy is there for them. So the energy of these two atoms is about this much. It is the energy of these atoms when they are away from each other like this. So in this condition, what happened? The two atoms approached each other. The two atoms approach each other. So when the two atoms approach each other, what happens? The distance between the two nuclei will decrease now. So for here, it is the internuclear distance now. It is internuclear distance. So from here, okay, here the two atoms are away from each other. Here the two atoms are close to each other, contacting each other. Now in this case, what happened? Internuclear distance became less. Okay, internuclear distance became less. Now here, what happened to the energy here? At this point, energy became less here. Energy on y-axis became less. So energy becomes less when they come close to each other. When they come close to each other, two atoms, what happens there? There will be attraction between the nucleus of this atom and electrons of this atom, and nucleus of this atom and electrons of this atom. Because of attraction, the energy will be decreased. See, the energy is slowly decreasing like this. The potential energy is decreasing between, means for the atoms, when the internuclear distance between the two atoms is decreasing. So as internuclear distance decreases between the atoms, the attraction force develops between electrons and nuclei of two atoms, and then what happens? The energy will be lowered. Whenever energy is lowering, whenever energy is decreasing, what happens to the stability? Stability will be increasing. Whenever energy is decreasing, stability of the species will be increasing. Remember. So like that, the energy slowly decreases to one minimum value. Okay. So here the energy decreased. So this distance now, this internuclear distance between the two nuclei is called the bond length. Bond length. So the bond length of hydrogen, what your molecule is what now? 74 picometers. So 74 picometers means 74 into 10 power minus 12 meters. So the bond length between two hydrogen nuclei, between two hydrogen atoms, the bond length is how much? 74 picometers. 74 picometers. Is the concept clear? So the same thing is 0.74 angstroms. 0.74 angstroms we can say, 74 picometers we can say, because 1 angstrom is equal to 100 picometers. 1 angstrom equals to 100 picometers. Now in this case, what happened? Tell me. Two atoms overlapped with each other. The orbital, s orbital of this hydrogen, s orbital of this hydrogen. So both of these hydrogen atoms. Okay. So when s orbital and s orbital overlap with each other, this is ss overlap. Between s orbital of hydrogen, s orbital of hydrogen, it is what? Ss overlap. Because of ss overlap, what happened? The distance became very less. When the two nuclei come very close to each other, when the distance is less between two nuclei, the repulsion starts now. Repulsion between nucleus and nucleus, repulsion between electrons and electrons of two atoms. Whenever repulsion starts, suddenly the energy will be increasing. the steep increase, the sudden increase in the energy will be observed here. The energy will be increasing because of repulsion, remember always. Because of attraction, what happens here? Why energy is decreasing? The energy is decreasing as the two atoms approaching each other due to what? Attraction between two nuclei, between nucleus and electrons. Due to attraction, always energy will be decreased and stability will be increased. And here what happened when the distance is very less? Okay, very less distance is there between two atoms when they have overlapped with each other. When they overlap with each other, the distance is very less here. In this condition, what happens now? Nuclei will repel each other, electrons will repel each other from two atoms. Therefore, suddenly, due to repulsion, energy will be increasing like this. So this is what now here at this distance, the distance at which between the two nuclei, the two atoms, two atoms are held together by a chemical bond. Is called what? This distance is called what? Bond length. Okay. Next, orbital overlap concept is important concept in chemical bond. This is one p orbital. This is one p orbital. This p orbital has two lobes. This p orbital also has two lobes. And this is positive lobe of this p orbital, negative lobe of this p orbital. Generally, positive lobe represents what? Crest of the electron wave, and the negative lobe indicates what? Trough of the electron wave. Electron wave will have crest and trough, right? So crest and trough generally we imagine. So in this case also, in this p orbital also, the dumbbell shape with positive lobe and negative lobe there. When two orbitals pz and pz, we are taking what? This is nucleus of atom, this is nucleus of one atom, and this is nucleus of another atom. So between these two nuclei, the line joining is which axis is taken here? Z axis is taken as what? Internuclear axis. Internuclear axis means the axis between the nuclei is taken as what? Z axis. So when Z axis is internuclear axis, the pz orbital will be oriented. Oriented means the arranged. Okay, arranged along the same axis. Along the same axis, both orbitals are there. Now what happens between these two? Axial overlap takes place because this p orbital, both are on same axis now. So this type of overlap between two p orbitals is called axial overlapping. Axial overlapping, or we say what? Axial overlapping, otherwise linear overlapping. Linear overlapping or axial overlapping we say. Okay. So because of axial overlapping or linear overlapping, which bond is formed between these two? Sigma bond is formed. Axial overlap will lead to the formation of what? Sigma bond. So in this case now here, positive lobe versus positive lobe. This is called what now here? Positive overlap. Positive overlap we say. So whenever positive lobe is on positive lobe overlapping, this is what now here? Positive overlap. That means what? This electron wave of this orbital and electron wave of this orbital, both are in the same phase. Same phase meaning what? The crust is falling on crust. Crust is falling on crust. This type of what here? Two waves of two orbitals called what? Electron waves are called what here? They are in phase. The two electron waves of these two orbitals are in the same phase. Therefore, this type of overlap is called positive overlap. Then bond will be formed between this nucleus and this nucleus. Next, if you take this type of diagram, here overlapping is between S and P orbitals. This one PP overlapping. Here S and P orbital. Anyhow, S orbital will be having what? Positive lobes, two lobes not there here. It is spherically shaped. So here positive means what now? Here a crust of this electron wave, and it is crust of another electron wave of p orbital. So here it is what now? Trough. It is crust. Now crust of one electron wave of p orbital and crust of electron wave of s orbital, both are overlapping with each other. Therefore, what happens now here? Positive overlap we can take here. Positive, no? So positive overlap. Positive overlap means this electron wave of s orbital, the electron wave of p orbital, both are in the same phase. Same phase means crust falling on crust. Okay. So next one, in this case now, two p orbitals. This p orbital, px orbital we have taken. What is this? Px. Px means what now here? It is the x-axis taken. This is z-axis now. This is z-axis and x-axis taken here. So x-axis and z-axis when you take here. So this axis is taken as what? Z-axis. This one is taken as what? X-axis. Okay. So along the x-axis, if p orbital is there, that is called what now here? Px orbital. Px orbital. So here px orbital, both are parallel to each other. This orbital, both are what? Parallel to each other, not along the same axis. They are parallel to each other. Now this px is perpendicular to axis, internuclear axis. Here internuclear axis is dead axis here. It is nucleus, it is also nucleus. So between the two nuclei, this axis is called internuclear axis, that is dead axis. And this p orbital, px orbital is perpendicular to what? Internuclear axis. So both p orbitals are what now here? Both p orbitals are parallel to each other. When two p orbitals are parallel to each other, what happens? Sideways overlap will take place, or axial overlap will take place here. Sideways overlapping will be taking place here. Sideways overlapping. So sideways overlapping meaning what here? Lateral overlapping. This lateral overlapping will lead to the formation of what? To the formation of what? Pi bond. So pi bond is formed here. Pi bond will be formed. Is that clear, ma'am? So pi bond is formed between two p orbitals when they are overlapping sideways. This is pi bond between two p orbitals. It is also pp overlap. Remember, pp overlap. This one also pp overlap. This pp overlap of axial overlapping will lead to the formation of sigma bond. This type of lateral overlapping of two p orbitals will lead to the formation of pi bond. So it is pi pp bond. Here pi sigma pp bond. Sigma pp bond will be formed here. Pi pp bond will be formed here. Here what is formed? Sigma or pi between s orbital and p orbital. Whenever s orbital is involved, always what will be forming? Sigma bond only is possible. Whenever s orbital is involved, only sigma bond is possible. And also remember, hybrid orbitals. Whenever hybrid orbital is involved in overlapping process, that must be forming what? Only sigma bond. Suppose when any hybrid orbital versus s orbital, any hybrid orbital versus p orbital, always it must be forming what? Sigma bond only. S orbitals and hybrid orbitals cannot form pi bond. Okay, so this point we have to keep in mind. Next, so if you take this one here, in this case now here, pz orbital, both p orbitals only. Both are present along the same axis. Now here, this is the negative lobe of p orbital. This is positive lobe of p orbital. Positive lobe means what we have to consider? Crust. And negative lobe indicates what? Trough. Now crust of one electron wave of p orbital is falling on trough of the electron wave of another p orbital. So this type of overlapping is taken as negative overlap. Negative overlap we say. And this electron wave both are said to be out of phase. The electron wave of this orbital, are said to be out of phase. That point keep in mind. It is negative overlap. When positive lobe overlaps with the negative overlap of two p orbitals between two p orbitals, this type of overlap is called negative overlap. Keep in mind. And here, so the negative lobe is overlapping with positive lobe. Positive of what? S orbital. Anyhow, s orbital will have positive end only. Positive and here negative. Means the trough is falling on crust. Trough is falling on crust of another electron wave. So it is also negative overlapping. And here also positive lobe versus negative lobe. It is also negative overlap. Next, in this case, positive, negative. So it is positive overlap. Will form this type of bond here. Okay. Next one here, negative overlap. This one, negative overlap. It is positive overlap. Keep in mind. So these two p orbitals are parallel to each other. These two also parallel to each other. But here positive overlap is taken or negative overlap is taken? Negative overlap. Why negative overlap? The positive lobe is overlapping with negative lobe here. That means crust is falling on trough. So it is what now here? Negative overlap. Keep in mind. And here also. Now py and py. So we have taken here. This one is vertical is what? X-axis. The horizontal is z-axis. And this slanting is what? This one y-axis we are taking. So along y-axis, one dumbbell shape. Along y-axis of another atom, one dumbbell shape. It is from one atom. Now the two py orbitals of two atoms Okay, or perpendicular to x-axis, means what, axis, z-axis. Then this p orbital, that is py orbital versus py orbital, how they are oriented, how they are arranged, parallel to each other. When two p orbitals are parallel to each other, sideways overlap takes place. Sideways overlap will lead to the formation of sigma bond. So therefore here sigma bond or pi bond? Pi bond will be formed here. Axial overlapping will be forming sigma bond. Lateral overlapping will be forming pi bond. So here between this py and py, which type of bond is possible? Pi bond is possible because of lateral or sidewise overlapping. Now here positive lobe versus positive lobe. So it is positive overlap. So this positive overlap between py and py orbitals will form what? Pi bond. pp, pi bond. Between p and p, pi bond. It is one nucleus, it is one nucleus. It is internuclear distance, internuclear axis. So this way positive overlap and negative overlap is very important to understand. Next, we also have zero overlap. Zero overlap means, here see, this is px double shape, px orbital, okay, along x-axis of one atom, and it is what now s orbital of another atom. S orbital from one atom, px orbital from other atom. When these two orbitals approach each other, here these two atoms, these two orbitals are neither parallel to each other nor along the same axis. Proper orientation is not there between these two orbitals. There is no proper orientation, meaning what? These two orbitals, s and p orbitals here, are neither parallel to each other nor along the same axis. Therefore, the linear overlapping is not possible as they are not on the same axis. Sidewise overlapping is also not possible as they are not parallel to each other. Therefore, overlap only is not possible here. There is no possibility for overlap between this type of orbitals. So it is what zero overlap we say. Zero overlap here. Though it is plus and plus here, though we have written plus and plus here, it is zero overlap we say. Zero overlap meaning what here? When two orbitals are not having proper orientation, proper arrangement, in that case they cannot undergo overlapping process. Next, here also same thing. Here it is px. Px is what now? Along x-axis, double shape along x-axis. It is py, double shape along y-axis. Okay. Now px and py orbitals are neither parallel to each other exactly nor along the same axis. Therefore, these two also cannot overlap with each other. Though plus and plus lobe there here, they cannot overlap. Why? Because it is along the y-axis, it is along the x-axis. They are not parallel to each other. Actually, they are perpendicular to each other. When they are not parallel to each other, they cannot overlap, form the bond. Next, we have three types of overlaps we discussed. PP overlap, SS overlap, SP overlap. Which overlap is stronger than which one? Which overlap is having more strength than which one? PP overlap stronger than SP overlap, stronger than SS overlap. Remember, PP overlap is stronger. Why? The p orbitals are directional orbitals. They have specific direction. P orbitals have what? Specific direction along x-axis, along y-axis, along z-axis. Because of directional character of p orbitals, when PP overlap is taken, it is more stronger bond. It will give a stronger bond than SP overlapping, than SS overlapping. So here p orbital, when they overlap with each other, that is called PP overlapping. Here these two p orbitals are along the same axis now. Along the same internuclear axis, these two are taken here. When two p orbitals are along the same axis, they will undergo axial overlapping or linear overlapping to form what? Sigma bond here. So which type of bond is possible here? Sigma bond is possible here. Sigma bond is between p and p. So sigma pp bond we say here. And it is also pp overlap, but in this case what happened? It is this p orbital, both are what? Parallel to each other. So this is PP overlap, that is parallel overlapping, lateral overlapping. It will form what? Pi bond here. So this pi bond will have how many electron clouds? Each pi bond will have two electron clouds. One electron cloud above the axis, one electron cloud below the axis. Below the internuclear axis, one electron cloud, above one electron cloud. That means what? Above the plane, below the plane, the electron cloud of pi bond will be oriented. Okay. Next, if you take the concept of hybridization, we discussed about hybridization. In hybridization, what happens? We have different types of hybridization. Like example here, we have taken sp3 hybridization. In case of sp3 hybridization, one s orbital intermixes with 3 p orbitals. Here, s orbital is mixing with the 3 p orbitals, px, py, pz. So this is taken as what? Z axis, internuclear axis, Z axis. Is vertical is what? X axis taken. It is Y axis. Okay. So this s orbital and 3 p orbitals will mix with each other to give 4 hybrid orbitals. These 4 hybrid orbitals have what? Same energy and same shape. Here s orbital spherical shape, p orbitals dumbbell shapes. When these all mixed, we get club club shaped orbitals called hybrid orbitals. Here it is, these are called what? sp3 hybrids. sp3 hybrid orbitals. So between any two sp3 hybrid orbitals, what is the bond angle? 109 degrees 28 minutes. That is 109.5 degrees. And what is geometry of orbitals here? The orbitals of this sp3 will take the geometry of tetrahedron. Tetrahedron is the geometry. So they have tetrahedral geometry. sp3 hybrid orbitals have tetrahedral geometry. Like this, every hybridization give what? Every hybridization gives what? Different types of orbital geometries. So now in this case, all the 4 sp3 hybrid orbitals are not in the same plane. They are in different planes. That's why the tetrahedral geometry is non-planar geometry. It is not planar, non-planar geometry, tetrahedral. And in this case, the 4 sp3 hybrid orbitals of carbon, suppose in methane, CH4, the 4 sp3 hybrid orbitals of methane, means carbon, will overlap with what? S orbitals of hydrogen atoms, like this. So in this way, sigma sp3, yes, sigma sp3, S bond will be formed here. Like this, 4 bonds are formed. And we have different types of molecular shapes: square planar geometry, square planar shape, trigonal bipyramidal, square pyramidal, octahedral, like this. Now, square planar will take which type of hybridization? dsp2. In this dsp2, what will be mixing? 1 d orbital, 1 s orbital, and 2 p orbitals will be intermixing. Okay. And examples what here for this type of hybridization? Nickel tetracyanide. Nickel tetracyanide. It is NiCN4 minus 2. But don't confuse that. NiCO taken 4 will be there. NiCO taken 4. 0 charge here. NiCO taken 4. That is what? Nickel tetracarbonyl. CO group is what? Carbonyl group. Carbonyl group. So NiCO taken 4 is what? Nickel tetracarbonyl. Nickel tetracarbonyl. So the nickel tetracarbonyl will be what your example what for what sp3, remember. NiCO4 will be sp3, but NiCN taken 4 minus 2 is what? dsp2, remember. So PtCl4 minus 2, platinum tetrachloride with minus 2 charge is also what? Square planar geometry. And trigonal bipyramid sp3d hybridization, in this 1 s orbital, 1 d orbital, 3 p orbitals will mix. Examples PaCl5, PF5. And square pyramid, it will be sp3d2. Okay, here these are mixed here, orbitals are mixed. And example BrF5, this is what? Bromine pentafluoride. This compound is between 2 halogen atoms, between 2 halogens. So it is called interhalogen compound. Interhalogen compound. Between 2 halogens, the compound formed here. And octahedral also what? sp3d2 we can say, or d2sp3 we can say. So in this case now here, examples what? SF6 sulfur hexafluoride and chromium hexafluoride minus 3, and carbonyl means what? Cobalt NH3 taken 6 here. Cobalt hexaamine with positive charge cation it is. So the naming of these what here complexes is different concept that we will discuss later. Naming of these compounds. Next, if you take another important concept of this lesson, what? Molecular orbital theory. So in this case now here, when s orbital, 1 s orbital and 1 s orbital of 2 atoms combine, we get 2 molecular orbitals. Okay, one is what? Without star called bonding molecular orbital. Another one is what? Anti-bonding molecular orbital. Here s orbital and s orbital always will overlap by axial overlapping, and always they will form sigma bond only. That's why a sigma 1s, a sigma star 1s. A star indicates for high energy and anti-bonding molecular orbital. So it is anti-bonding molecular orbital, it is bonding molecular orbital. Between these two, what will be having less energy? Sigma 1s will have lesser energy than sigma star 1s. Now remember here. So this is energy of what? This is the energy of atomic orbital. 1s orbital and 1s orbital of two atoms have same energy. This much energy is there. Now the energy of what? Anti-bonding molecular orbital is what? More, very high. And the energy of this bonding molecular orbital is less than AO. So this bonding molecular orbital has lesser energy than what? AO. Anti-bonding has more energy than AO. Now see the difference here. The increase in the formation, the increase in energy in the formation of anti-bonding is more. The decrease of energy in the formation of BMO is more. What I'm asking is the increase in the energy in the formation of anti-bonding molecular orbital is more, or the decrease in the energy of formation of BMO is more. This one is more. Here energy gap is more, you see. That means when atomic orbital 1s and 1s combine with each other, okay, the nucleus and nucleus, this nucleus, electrons and electrons will repel each other now. So because of repulsion, the increase in the energy will be greater than what? The decrease in energy. Remember, the increase in energy will be greater than decrease in energy. Okay, the increase in the energy due to during formation of ABMO will be greater than the decrease in energy in the formation of BMO. That point keep in mind. That's why we have not written same length, same distance. Here energy gap is more, here energy gap is less. Okay, so this point keep in mind. Next, so 1s and 1s orbitals when they combine, we have two types of molecular orbitals here. It is ABMO, it is BMO. Here BMO is what now without star. So here any node is there between the nuclei? No, there is no node. This nucleus and this nucleus, they are bonded together here. And here in this case now here, between this nucleus and this nucleus, some gap is formed, you see. This is zero electron density. This line is what? The plane is with zero electron density. This plane with zero electron density is called what? Node. Nodal plane. This is nodal plane, otherwise node. So how many nodes here? One node between the two nuclei. Zero electron density here. So how many nodes will be present in sigma star 1s? One node. This sigma bond, sigma orbital, na? Sigma molecular orbital. Sigma star molecular orbital will always have one nodal plane, one node, we say. If you take sigma star 2s also, sigma star 2s also will have one nodal plane. Okay, and it is sigma 1s. Sigma 1s has no nodal plane, no zero electron density here. Here it is sigma means BMO. So sigma BMO has no nodal plane, zero nodal planes. But sigma star 1s means anti-bonding molecular orbital of sigma type will have one nodal plane between the two nuclei. Nodal plane means what? The zero electron density. Next here. Now if you take 2px versus 2px, when 2px and 2px combine from two atoms, two types of molecular orbitals will be possible to form. It is what pi 2px may be formed, pi star 2px may be formed. When 2px and 2px overlap with each other, we get what? Pi 2px, pi star 2px, suppose, between two p orbitals. In this case, it is pi star 2px means what? It is what? Anti-bonding molecular orbital. Anti-bonding molecular orbital. So this anti-bonding molecular orbital has how many nodal planes, you see? This is one nodal plane between two nuclei, and it is another nodal plane, remember. It is another nodal plane. So two nodal planes there here. This is one nodal plane between, and this is one nodal plane. So how many nodal planes will be present? How many nodes will be present in sigma means pi star 2px? Two nodal planes will be there. That means what? Pi anti-bonding molecular orbitals. Pi anti-bonding molecular orbitals will have what? Two nodal planes in each. Not only this pi star 2px, pi star 2py also will have two nodal planes. Okay, that is what important thing to understand here. Now, if you take this one, here between 2px, we also get what? BMO, bonding molecular orbital without star here, pi 2px. In this case, between the two nuclei, only one will be there, one nodal plane will be there, one zero electron density plane will be there. How many nodes for the pi BMO? Pi BMO, only one nodal plane. But pi star BMO has two nodal planes. So the number of nodal planes is important concept. Now, so this is the order of what? Molecular orbitals. Okay, here for the molecules such as B2, C2, N2, we get sigma 1s less than sigma star 1s less than sigma 2s less than sigma star 2s less than pi 2px equals to pi 2py less than sigma 2pz less than pi star 2px equals to pi star 2py less than sigma star 2pz. In this order, y equals to symbol here. Why the symbol is taken? Because the energy of pi 2px is equal to energy of pi 2py. The same thing here also. Now these two orbitals have same energy but different directions along x-axis, along y-axis. Different directions there but same energy there. So these two are called degenerate orbitals. These two also called degenerate orbitals. Here it is what pi without star. Without star here. It is what now pi BMO. These two pi BMO have what? Same energy. These two pi star ABMO. Pi star ABMO have what? Same energy. But different directions. They are degenerate orbitals. Okay. This is for this. Why here this order is there in this case? Because the 2s orbitals intermix with the 2p orbitals. The energy gap between 2s orbitals and 2p orbitals is less in these molecules. Because of less energy gap, they immediately what? Combine with each other, intermix with each other, repulsion will take place, and the sigma 2pz will get more energy. The sigma 2pz gets more energy than what? This pi 2px and pi 2py. Than pi 2px and pi 2py, the sigma 2pz will have more energy because of mixing of 2s orbitals and 2p orbitals in nitrogen molecule. Why 2s 2p mixing is taking place means the energy gap between 2s orbitals and 2p orbitals of these molecules will be less. Because of less energy gap, 2s 2p mixing takes place. 2s 2p interaction takes place there. But in O2 molecule, F2 molecule, neon molecule, in these cases, what happens now? The energy gap between 2s orbitals and 2p orbitals will be high. When energy gap is more, what happens there? The intermixing between 2s orbitals and 2p orbitals does not take place. Interaction does not take place between 2s and 2p. So due to lack of 2s 2p mixing, here the energy order will be this one. Here sigma 2pz will have lesser energy than what? Pi 2px equals to pi 2py. Than pi 2px and pi 2py, sigma 2pz will have lesser energy in case of O2 F2 and Ne2. But this will be taken after pi 2px, pi 2py in case of N2. Only that is the difference. And last topic is what important area? Hydrogen bonding. Hydrogen bonding is of two types, I told you. Intermolecular hydrogen bonding, intramolecular hydrogen bonding. Inter means between two molecules. Intra means within same molecule. So intramolecular hydrogen bonding, example we have taken here. Benzene ring with OH group is called phenol. Benzene ring with OH group is called phenol. Here OH group wherever is attached, that will be taken as first carbon, and this one will be taken as second carbon. Now on second carbon, what is there? NO2 group is there. NO2 means nitro group. NO2 group is attached to second carbon. To the first carbon, what is attached? OH is attached. OH group, alcohol group is attached. Now here, what we have to understand is that the hydrogen atom of OH group and oxygen atom of NO2 group will be bonded with what now? Hydrogen bonding here. There will be weak electrostatic attractive force between H and O. Here oxygen is electronegative atom, hydrogen is electropositive atom. Between these two, electrostatic attractive force will develop. This attractive force between hydrogen and more electronegative atom, such as fluorine, oxygen, and nitrogen, is called what? Hydrogen bonding. So this hydrogen bonding is within the same molecule. No? That's why it is called intramolecular hydrogen bonding. And if you take water molecule between H2O and another H2O molecule, what will be there? Intermolecular will be there in that case. Inter means between the molecules. HF, HCl, NH3. You take as what? Intermolecular hydrogen bonding. And it is what now? 2-nitrophenol. Benzene with OH group is called phenol. So 2-nitrophenol it is. A second carbon nitro group is there. And also I told you, this alpha carbon, this one is alpha carbon because the main group OH group is attached here. This first carbon is taken as what? Alpha carbon, and this carbon should be taken as beta carbon. It is what now? Second position is what now? Beta carbon. So this beta carbon has what? NO2 group. So beta nitrophenol we can say. Also we can say ortho position. The second position is ortho, I told you. Orthonitrophenol, beta nitrophenol, 2-nitrophenol. Right, ma'am? Okay, have a good day.